In the deep dark between galaxies, time leaves a quiet signature. Light travels for billions of years and arrives carrying a single question. Is the universe slowing down or speeding up? Tonight, the evidence unfolds in calm layers. Distant supernovae, expansion history, the subtle growth of the cosmic web. Each clue is gentle on its own. Together they reveal a universe that begins to accelerate. Deep space drift follows that curve through silence and scale. From nearby starlight to the farthest background glow, the story settles into a steady rhythm. A faint point inside a far galaxy brightens, then fades with patient regularity. That rise and fall becomes a ruler for expansion when its true brightness is known. At this distance, a spiral galaxy is a soft whirl with dark dust lanes. Its arms look like thin brush strokes against a deeper black. Near the edge of one arm, a point swells into a pale glow. The glow does not stay sharp. A thin shell of hot gas expands outward and cools. In projection, it can resemble a dim ring with a brighter rim. The rim thickens, then softens into a wider haze as time passes. The pattern comes from a specific kind of stellar explosion. It begins with a compact remnant that holds close to a strict mass limit. A white dwarf is a compact stellar core supported by electron pressure. When material accumulates beyond a threshold, fusion runs away. The star unbinds itself in moments while light leaks out for weeks. The debris expands in layers. Faster material runs ahead. Slower material lags behind. A steep gradient forms where hot gas thins into colder space. A light curve is brightness traced over time. In this class of explosion, the curve has a dependable shape. Brighter events fade more slowly. Dimmer events fade more quickly. That link allows a correction. Once corrected, the true brightness becomes tightly constrained. A standard candle has known intrinsic brightness. When intrinsic brightness is known, apparent brightness reveals distance. The rule follows from geometry. Light spreads over a growing sphere as it travels. Twice the distance means roughly 4 times the dimming. The idea feels like marks on a rubber sheet as it is stretched. The marks remain fixed to the sheet. The spacing grows anyway. Space changes the separation without sliding any mark across the surface. In the same calm way, corrected supernova brightness becomes spacing on a cosmic map. The map is not drawn on paper. It is drawn in the faintness of light arriving from different eras. A second ingredient is the stretching of that light by expansion. Light behaves as if each wave crest is pulled farther from the next. Colours drift toward longer wavelengths. The host galaxy looks older and softer at extreme distance. Fine features smear into broader bands. The supernova fade also appears slower. The rise takes longer. The decline takes longer. The same physical event is seen through an expanded interval of time. This slowing is not a local effect. It accumulates along the whole path the light takes. With distance and stretching in hand, a quiet test becomes possible. The test compares how far an event seems with how stretched its light appears. If the universe holds matter alone, gravity should slow expansion over time. In that history, the distance stretching relation follows a decelerating curve. Early on, expansion is faster. Later, it slows as matter gathers and its pull adds up across space. The curve bends gently. It predicts how bright a standard candle should look at each level of stretching. Then the evidence arrives as a persistent mismatch. Many distant supernovae appear slightly dimmer than a breaking curve predicts. The difference is subtle. It repeats across many separate host galaxies. Dimmer at fixed stretch means farther than expected. Farther than expected at fixed stretch means expansion has grown more than a slowing history allows. Over billions of years, the curve bends the other way. Expansion stops losing speed and begins to gain it. The conclusion does not need a dramatic jump. It needs consistency across many faint points. A slow scene returns to keep the idea anchored in matter and shape. Between two galaxy clusters, a sparse region opens into deep darkness. The clusters are not smooth spheres. They show layered halos with denser cores. Filaments connect them as faint bridges. Between the bridges, voids widen like basins in a black landscape. In one small galaxy along a filament, another supernova blooms. Its light crosses an outer haze that is not uniform. Streaks of dust form thin curtains. Those curtains scatter blue light more than red. A dim shadow of extinction falls across part of the host. Past the host, the light enters a cleaner void. There it spreads and cools, and it arrives later than a nearby twin would. A small payoff settles into place. The dimness cannot be blamed on simple distance alone. The stretching already accounts for geometric spreading and time dilation. When dimness still exceeds that prediction, the distance must be larger. A larger distance at the same stretch is the signature of extra expansion. A limit of observation sits inside this method, and it must be faced softly. The mind wants a single decisive flare. The evidence is a trend built from many. At the greatest distances, a flare can blend into its host galaxy's background glow. Intrinsic variation can survive the correction at low level. Dust can hide light and imitate extra distance. Weak gravitational lensing can brighten or dim a flare by a modest amount. These effects do not announce themselves. They add scatter around the curve. The limit is concrete. Light becomes too faint to separate cleanly from its surroundings. The curve must be inferred with care because the signal approaches the edge of clean measurement. Even with that boundary, the central message stays plain. The best corrected candles in deep space sit too faint for a universe that only breaks. The offset grows with distance in the way an accelerating history predicts. A single number gives the story a place in time. The shift toward acceleration becomes important about 5 billion years ago. That's about half the age of the Sun. Before that era, matter dominates the expansion budget and slows it. After that era, a different influence becomes noticeable on the larger scales. The influence is not seen as a local push. It is seen as a slow reshaping of the distance stretching curve across the sky. The next step is to ask what else could mimic this curve. Dust and blur are one answer. The nature of expansion itself is another. A distant explosion can look faint for more than one quiet reason. Dust between stars can dim and redden the light, and that effect must be untangled before distance can be trusted. In that region, a galaxy presents a thin, dark lane across a pale bulge. The lane has a sharp edge on one side. It feathers into a softer boundary on the other. The boundary is not smooth. It shows clumps and gaps like torn fabric in slow motion. A fading supernova glows near the lane. The glow seems to sit behind a veil. Its outer halo looks wider than expected as scattered light forms a faint aureole. The first small understanding settles quickly. A candle can appear weaker without being farther away. Interstellar dust is tiny, solid grains floating between stars. The grains are often about 1/1,000,000th of a meter across. That size is like fine smoke in sunlight. When light crosses such grains, blue light scatters more than red light. The remaining beam shifts toward warmer colours. The same beam also loses total intensity. This paired change is called extinction and reddening. It matters because distance estimates rely on brightness. A second slow image keeps the idea grounded in shape and boundary. Along the dust lane, the supernova light crosses layers of differing thickness. A thinner patch lets more light through. A thicker knot casts a deeper shadow. The shadow has a curved outline because the lane is a sheet seen at an angle. The supernova does not change its physics. The view changes because the path through the lane changes. Even a modest extra layer can remove a noticeable fraction of light. The clue appears in colour. If the light grows redder than the known pattern, dust becomes a likely cause. If the colour stays normal, but the event is faint, distance becomes more likely. Another small understanding arrives. Colour can separate dimming by dust from dimming by distance. This separation is not perfect. It is a disciplined guess based on how dust behaves. A light curve already provides a timing pattern. Colour adds a second axis. The method compares the observed colour evolution to the expected one. When the curve is too red at multiple phases, a correction is applied. The The correction estimates how much light is removed. It then restores the brightness closer to what would be seen in clearer space. The analogy is a landscape seen through tinted glass. The scene behind the glass does not change. The perceived brightness and hue change together. If the glass tint is measured, the true scene can be reconstructed. The same logic guides dust correction for supernovae. A different view of the same galaxy deepens the sense of scale. At the outskirts, stars thin out and the background darkens. Dust becomes less common. A supernova in the outer halo has a cleaner path. Its light looks bluer and crisper. Its fading halo has a tighter rim. The contrast between rim and background is sharper. This is not an aesthetic detail. It changes how reliable a candle becomes. The practical point becomes clear without heavy machinery. Supernovae in clearer lines of sight offer tighter distance estimates. Supernovae behind complex lanes carry more uncertainty. Another small understanding clicks into place. Choosing cleaner environments reduces error without changing the physics of the explosion. That choice shapes the final data set. Here a limit of observation enters gently. At large distances, galaxies blur into small patches. Dust lanes become unresolved. Clumps and sheets blend into one dim gradient. The line of sight cannot be mapped in detail. The colour also becomes harder to measure cleanly. Faint light arrives with more noise. The limit is specific. Dust geometry becomes invisible when the host is too small and too faint to resolve. The correction then relies on average dust behaviour. An average cannot capture every knot and gap. Some events will be overcorrected, some will be undercorrected. The scatter grows with distance. This boundary does not destroy the method. It defines the level of trust at the far edge. A slow scene of light crossing a diffuse region helps the boundary feel physical. Between spiral arms, dust spreads into a thin mist. The mist has a soft gradient rather than a hard edge. Through it, the supernova light develops a faint extended glow. The glow is not a second source. It is scattered light arriving along slightly longer paths. Those paths delay the light. The delay stretches the apparent fade in subtle ways. The effect is usually small. It matters when precision becomes the goal. Another small understanding settles. Dust can influence both brightness and the apparent timing. That influence must be separated from the true cosmic stretching of time. This is why multiple checks are used. The colour evolution is one check. The shape of the light curve is another. The host environment provides a third. A scale shift carries the mind from grains to the whole sky. A single grain is smaller than a cell. A dust cloud spans many light years. A galaxy contains thousands of such clouds. Across billions of light years, countless clouds lie along different paths. Each path has its own hidden layering. Yet the statistical behaviour remains stable enough to model. The stability comes from the physics of scattering. It depends on grain sizes and compositions that vary within limits. Those limits create a predictable relationship between dimming and reddening. That predictability is why correction works at all. Another small understanding arrives. The correction is not a guess at distance. It is a constrained adjustment based on how light interacts with small solids. Even so, caution persists. Dust is not the only source of dimming. Weak gravitational lensing can dim or brighten. Intrinsic variation can slip through correction. Selection also matters. The faintest events can be missed at great distance. The absence can bend inferred trends. The limit here is also specific. A sample can become biased when detection favours brighter events. Bias can mimic or hide subtle curvature in the distance relation. The remedy is to model the selection and include its uncertainty. This keeps conclusions from leaning too hard on the faint edge. The section returns to the galaxy lane one last time. The lane shows a serrated boundary. A thin filament peels away from the main sheet. The filament creates a narrow shadow that crosses the supernova halo. The shadow fades with distance from the lane as the filament thins. The physical picture is simple. Dust acts like a filter with thickness that varies in space. Correcting for that filter is like restoring the original candle before reading its distance. With the candle cleaned, the next checkpoint becomes the stretching of the spectrum itself. In that region, light lengthens on its journey. The next section follows that stretching into the history of expansion. A spectrum from a distant flare arrives, stretched as if its colours have been gently pulled apart. That stretching, called redshift, records how much space grows during the light's journey. At this distance, the host galaxy is a faint oval with a soft core. Its outskirts fade into darkness without a clear edge. A supernova glow rises within it. The glow carries a mix of colours that would form a smooth band. Along that band, certain colours are reduced where atoms absorb light. Those absorption dips act like notches in a long ribbon. The notches do not stay fixed. They slide toward redder colours when the source is farther away. The slide is not a trick of dust. Dust dims and reddens, but it does not shift every notch together. A small understanding settles early. When all notches shift as a group, space itself is stretching the light. Redshift is a fractional stretch of wavelength. The definition can be kept short. Redshift is the amount a wavelength lengthens during travel. Imagine a line of ripples on a pond. A steady breeze can pull the ripples farther apart. The crests become more widely spaced. The pattern remains a pattern only stretched. The same happens to light waves moving through expanding space. The stretching affects time as well. The supernova rise and fade appear slowed by the same factor. A pulse that takes days in its own frame appears to take longer when redshift is large. This is not because the explosion is lazier. The path has more expanding space embedded in it. That simple link yields a second small understanding. Redshift measures both colour shift and apparent time stretching with one cause. A new visual anchor keeps the idea concrete and slow. A long beam of light crosses a vast void. The void is not empty in a dramatic way. It is a thin darkness with sparse gas and faint background glow. Along the beam, the wave crests start close together. Farther along, the spacing grows. The beam keeps its direction. Its amplitude slowly weakens as it spreads. Its internal rhythm slows because the wave spacing lengthens. The effect is gentle at any small segment. It becomes large after billions of years. Here a scale shift arrives without strain. A single wave crest spacing is smaller than a grain of dust. The same wave, after travelling for billions of years, arrives stretched by a factor of about 2. That is like a lullaby played at half tempo. The melody remains recognisable. The spacing between notes becomes wider. With that scaling, redshift becomes a cosmic clock. It sorts light by how long it travels. Higher redshift means older light. Older light means a younger universe at emission. This ordering lets expansion history be traced. The trace comes from pairing redshift with distance. Distance comes from corrected supernova brightness. Redshift comes from the shifted notches. Together they form a curve. The curve describes how fast space expands at different times. A third small understanding arrives. Distance and redshift together reveal not only expansion, but its change over time. A calm analogy sets the curve into a familiar picture without reusing earlier ones. Consider a long hallway with evenly spaced floor tiles. If the hallway could slowly lengthen, the tile spacing would widen. A mark on the far wall would recede faster later on if the stretching rate increases. In the sky, redshift plays the role of counting tiles. Brightness plays the role of how faint the far wall looks. The key is the relationship between the two. A simple universe with only matter produces one shape. A universe with late acceleration produces another shape. The curve's subtle bend encodes that difference. A slow scene of boundaries and gradients keeps the curve tied to physical detail. Around the supernova, expanding debris forms layered shells. The inner region remains hotter, longer. The outer region cools and thins. A steep gradient develops between bright inner layers and dim outer layers. As the debris expands, the gradient edge moves outward. The edge loses contrast as density drops. Those changes create evolving absorption notches. Certain layers absorb particular colours more strongly. As the layers thin, the notches weaken and broaden. This is helpful because it identifies the type of explosion. The pattern of notch evolution acts as a fingerprint. Another small understanding settles. The same physics that shapes the notches also confirms the candle type. This reduces confusion with other transient events. Now a limit of observation appears specific and gentle. At high redshift, the notches slide into redder light where the source may be very faint. The spectrum becomes noisy. Lines blur together. The notches can be mistaken or missed. The limit is one of resolution and signal clarity. If the notch depth is small compared to noise, the shift becomes uncertain. A small error in redshift can shift the inferred position along the expansion curve. The curve is shallow in places. Small horizontal errors can translate into larger ambiguity about the curve's bend. Another limit is physical. Not every supernova has identical notch strengths. Temperature and composition vary slightly. That variation can move the apparent notch center. The method then leans on averaging many events. The boundary is clear. Individual events near the faint edge carry wider uncertainty. The trend emerges only in a population. A quiet visual anchor returns to hold that population in mind. Across a field of distant galaxies, each appears as a smudge with a bright core. Some have fainter symmetry. Some have a darker lane hinted by a thin shadow. In several of them, a temporary point appears and fades. Each point contributes one pair of numbers. One is its redshift. One is its distance estimate. The pairs cluster along a band. The band is not a razor line. It has thickness from dust variation and lensing. Yet the band's centre drifts in a consistent way. A small understanding settles again. The power of the method comes from repetition across many lines of sight. Each sight line samples different dust and different structures. Shared curvature across them is difficult to fake. A final scale shift carries the mind from one notch to the whole history. One absorption dip is a tiny feature in a spectrum. Its shift becomes a marker of cosmic stretching. That stretching accumulates over distances so large that the host galaxies become faint stains. Over time, spans so long that stars are born and die many times over. Yet the message remains readable because the shift is coherent. It moves every notch together. The section closes with a soft handoff. With dust corrected and redshift measured, the next checkpoint is the cosmic map of filaments and voids. That map adds a different kind of ruler to the same expansion story. The larger structures in space look less like scattered islands and more like a woven fabric with dark holes. That fabric, the cosmic web, carries a quiet record of how expansion and gravity share control. At this distance, galaxies do not fill the sky evenly. They gather into long filaments that taper at the ends. They knot into clusters with bright cores and softer outskirts. Between them, voids open as broad cavities where only a few faint galaxies drift. The boundaries are not sharp walls. They're gradients where the density fades from crowded to sparse. Along a filament, the pattern resembles a strand of mist pulled into a rope. Around a cluster, it resembles a deepening glow with a rounded edge. A small understanding settles early. If expansion is faster, gravity has less time to pull matter into sharp knots. If expansion is slower, filaments tighten and clusters grow denser. The web therefore becomes a slow-motion ledger. It is written in shapes and contrasts rather than words. A second scene holds the ledger in a single image. A wide void sits like a bowl carved into darkness. Its rim is traced by a faint ring of galaxies. The ring is incomplete with gaps and thicker arcs. Those arcs mark places where filaments curve around the cavity. The cavity itself is not empty. It contains thin gas and a few isolated galaxies. Its center looks smoother than its rim. The physical detail is a boundary. Density changes most steeply at the rim, then relaxes inward. That boundary matters because it forms as matter streams outward from the void. It flows toward filaments, leaving the cavity broader with time. This sets a simple payoff into place. Expansion does not only stretch distances, it helps carve emptiness by allowing voids to widen while matter collects into edges. The next checkpoint is how such shapes appear across time. Older light shows the web at an earlier stage. Filaments look less contrasted. Clusters look less settled. Voids look smaller and less deep. Newer light shows thicker knots and wider cavities. The web therefore becomes a sequence, not a single snapshot. Expansion history is the rate of cosmic stretching over time. That definition stays short. Expansion history is how fast distances grow at each epoch. Imagine bread dough rising. The bubbles inside the dough widen. The thin walls between bubbles stretch and thin. If rising slows, the bubbles stop widening quickly. If rising speeds up, the bubbles expand more rapidly and the walls become more extended. In the web, voids are the bubbles, filaments are the walls. The analogy is not perfect, but it carries one calm truth. A faster stretch favours widening emptiness, while gravity still tries to keep walls thick. Another scene turns that balance into motion. Along a filament, small groups of galaxies lie like beads. Between bead groups, the filament narrows. The narrowing is a sign of flow. Matter drifts along the filament toward the nearest knot. The knot shows a layered halo. The inner region is compact. The outer region is diffuse and fades into the filament. The motion is not seen as a blur. It is inferred from how structure grows. A small understanding settles. Growth of structure is a competition between gravity and expansion. Gravity gathers. Expansion dilutes. The winner changes with time. Early on, matter is denser. Gravity has a stronger grip. Later on, matter thins. Expansion gains leverage. This is where the web ties back to supernova distances and redshift. Supernovae provide a distance scale at different epochs. Redshift orders those epochs. The web provides a structural scale visible as typical separations between filaments and voids. If distances are larger than expected at a given redshift, the same web should appear more stretched on the sky. If growth is suppressed, filaments should appear less sharply defined at the same epoch. These links allow cross-checks. The result is not a single measurement. It is a coherent story told by different patterns. A clear number offers a foothold without strain. A large void can span about 100 million light-years. That is like laying 1,000 large galaxies edge to edge. On that scale, a small change in expansion history leaves a measurable imprint in the spacing of structure. The number also carries a scale shift. A galaxy is tens of thousands of light-years across. A void is thousands of times larger. A void evolves over billions of years, while stars evolve over millions to billions. The mind moves from stellar lifetimes to the slow breathing of the web. Another scene keeps the breathing gentle. At the edge of a void, a filament arcs like a soft crescent. The crescent has a brighter spine and dimmer flanks. The spine marks where matter is densest. The flanks taper into the cavity. The taper is gradual like fog thinning. Along the spine, small subknots appear. Each subknot has its own halo boundary. The boundaries overlap, creating a layered appearance. This layering matters because it reveals hierarchical growth. Small structures merge into larger ones. The merging is slower when expansion outruns gravity. The next small understanding arrives. A universe that accelerates late can still contain a web, but the web's growth slows. Filaments remain, yet their contrast increases more slowly with time. Voids continue to widen, yet the flow of matter into knots becomes less effective. Now a limit of observation enters with a clear edge. The web is three-dimensional, but the sky is a projection. Depth must be inferred from redshift and distance estimates. Those inferences have scatter. Galaxies also carry peculiar motions from local gravity. Those motions can shift inferred depth slightly. The result is a smearing along the line of sight. Filaments can look longer than they are. Clusters can appear stretched into faint spikes. The limit is specific. The mapping from redshift to true distance is not exact because motion and expansion mix in the signal. This does not erase the web. It adds uncertainty to fine details. It means the web is best trusted in broad patterns rather than sharp microstructure at the far edge. Another calm scene restores the broad pattern. A cluster sits at a filament intersection, like a bright node. Around it, several filaments radiate outward at different angles. Each filament has a different thickness. One is a thick bridge with many galaxies. Another is a thin thread with only a few. Between two threads, a wedge of emptiness opens. The emptiness has a curved boundary that meets the node. That curvature hints at gravity shaping the flow. Matter tends to fall inward along the bridges. The bridges thicken near the node, then thin outward. This geometry creates a quiet payoff. Even without tracking motion directly, the shapes imply direction. Thickening toward knots implies inflow. Widening emptiness implies outflow from voids. Together they outline how gravity works against expansion in real space. The section then steps back to the expansion curve itself. Supernova distances suggest how fast space stretches. The web suggests how well matter can respond to that stretching. When the curve begins to bend toward faster expansion, structure growth begins to quiet down. The web still exists, but its tightening slows. The universe keeps stretching the empty regions. It leaves knots more isolated over time. The next section follows the point where supernovae grow systematically too faint for a simple slowing universe. The web provides the stage, the candles provide the timing. The faintness of distant supernovae does not shout, it accumulates like a soft drift. The accumulated drift points to an expansion that stops slowing and begins speeding up. At this distance, a field of galaxies lies scattered across a dark background. Each galaxy is a small smear with a brighter center and a fading rim. Over time, several of these smears host a brief bloom. The blooms rise and fall in a familiar cadence. Their light curves match the corrected shape for standard candles. Their colors follow the expected evolution once dust is accounted for. Yet their peak brightness arrives a little lower than a simple slowing universe predicts. The difference is not a single dramatic outlier. It is a collective offset that repeats. A small understanding settles early. When many corrected candles are consistently too faint at the same redshift, the distances are larger than expected. A slow visual anchor holds the key geometry. Imagine a long corridor of darkness with evenly spaced faint lamps. Each lamp is identical. The farther lamps look dimmer because light spreads. If the corridor itself quietly lengthens while light travels, the far lamps become dimmer than geometry alone would suggest. The lamps do not change. The corridor changes. In the sky, the lamps are supernovae. The corridor is the expanding space between galaxies. The dimness beyond expectation becomes a measure of extra stretching. The effect is modest per event. It becomes decisive as the sample grows. The distance redshift relation forms a curve. If the universe only contains matter and radiation, gravity should cause the curve to bend one way. It should indicate deceleration over time. Instead, the observed curve bends differently at late times. The bend implies that the stretching of space increases relative to the decelerating expectation. The simplest description is acceleration. Expansion acceleration is the increase of expansion rate over time. The definition can stay short. Expansion acceleration means distances grow faster as time passes. A familiar analogy sets the idea into daily experience without reusing earlier ones. Consider a long roll of tape being pulled from a spool. At first the tape moves steadily. Later the pull becomes stronger and the tape speeds up. Marks on the tape separate faster with time. Nothing on the tape pushes itself. The separation rate changes because the pulling changes. In the cosmic case, the change is not a hand. It is a property inferred from the curve. The payoff is immediate. The curve itself encodes whether separation slows or speeds up independent of any story about causes. A slow scene adds physical detail and boundary. Inside a distant host galaxy, the supernova debris expands into a halo. The halo has a brighter inner region and a dimmer outer skirt. The skirt edge is diffuse while the inner boundary remains more defined. As days pass, the defined boundary softens. The halo fades into the background of the host. This fading is measured in relative terms across time. The brightness at peak matters most for distance. The rate of decline helps correction. Once corrected, the candle's intrinsic peak becomes nearly standard. That standard allows comparison across redshift. The comparison reveals the offset. The offset is small, but it is systematic. Another small understanding settles. The strongest evidence for acceleration is not that the candles are faint. It is that the faintness grows with redshift in the precise way a bending curve demands. A scale shift arrives with a single calm number. The change toward acceleration becomes evident around 5 billion years ago. That is like turning the calendar back to a time when Earth is already old, yet galaxies are still forming many new stars. In the next billions of years after that pivot, the curve drifts further from the decelerating expectation. The shift is gentle. It is not a sudden jump. The universe does not switch modes in a sharp instant. It gradually changes which component dominates the expansion budget. Matter thins as space expands. Any component that stays roughly constant per volume would then become relatively more important. The curve reflects that transition without naming the component yet. A second, slow visual anchor keeps the sense of distance and time aligned. Light behaves as if it carries a timestamp. Higher redshift implies older light. Older light implies the supernova occurred when the universe is smaller. The candle's apparent faintness implies how much space grows after that moment. The pair acts like two coordinates. One orders time, one measures accumulated stretching. The curve traced by many pairs shows the history. Another small understanding settles. Acceleration is not measured as a local force. It is measured as a global pattern in how distance depends on redshift. Now the limit of observation enters specific and unavoidable. The candle correction is not perfect. Dust correction has residual uncertainty. Weak lensing can shift brightness up or down by a small amount. Selection effects can remove the faintest events. Host galaxy light can blend with the supernova and bias the peak. The limit is the ability to isolate a faint point from a faint background with finite resolution. At very high redshift, the host and the supernova can blur together. The inferred brightness can be slightly too high or too low. The redshift itself can also have uncertainty when spectral features are weak. These uncertainties widen the band around the curve. They do not automatically change its mean bend, but they demand careful modelling. Another limit is conceptual. The mind wants to picture a single expanding shell racing outward. Expansion is not an outward motion through space. It is the stretching of space between distant bound regions. That distinction is subtle. It can break intuition when trying to imagine acceleration. The safer picture remains the curve. The curve is the observable imprint. Another slow scene resolves the intuition gently. Two galaxies sit within the same filament. Their separation is modest compared to the cosmic horizon. Gravity within the filament can keep local structure coherent. Far beyond the filament, voids widen and separate filaments from each other. The acceleration signature lives on those larger scales. It is not a push that tears apart a single galaxy. It is a long-term change in the average stretching of empty regions. The physical detail is a gradient. Dense regions resist expansion more effectively. Sparse regions follow expansion more closely. Over time, the universe becomes more dominated by sparse volumes. The average behavior then shifts. Another small understanding settles. The evidence does not claim that everything accelerates uniformly. It indicates that the overall expansion history has a late-time bend consistent with faster stretching of large-scale distances. The section ends with a calm step forward. If the curve bends as observed, some ingredient beyond ordinary matter becomes necessary in the simplest framework. The next checkpoint asks how gravity and density should shape expansion in the first place and why deceleration seems natural before the bend appears. A quiet expectation sits beneath many cosmological models that gravity should gradually slow expansion. That expectation comes from the way matter gathers and deepens its pull as the universe evolves. At this distance, a rich galaxy cluster appears as a dense glow with a rounded boundary. The boundary is not sharp. It grades from a bright core into a wide, dim halo. Around the halo, thin filaments connect the cluster to other knots. The filaments look like faint strands. They taper as they recede into the surrounding void. The void is not a void of nothing. It is a region where the glow of galaxies thins until only a few remain. This scene contains the basic ingredients. Matter exists in concentrated cores and in tenuous bridges. Gravity acts wherever matter lies, and its influence reaches across the empty gradients between structures. A small understanding settles early. If matter dominates the cosmic budget, gravity acts like a persistent drag on expansion. The simplest picture begins with density. When the universe is younger, matter is packed more tightly on average. As space expands, matter spreads out. That thinning reduces gravity's average braking effect over time. Yet braking still exists as long as matter is the main contributor. This leads to a clear checkpoint. The expansion rate should decline as the universe grows. The decline should be stronger when density is higher. The story can be held by a familiar analogy that has not appeared before. Consider a smooth floor sprinkled with sand. A sliding block moves across it. At first the sand is thick, friction is strong, the block slows quickly. Farther on the sand layer is thinner, friction is weaker. The block still slows but less strongly. In the cosmic version, matter density plays the role of sand thickness. Gravity plays the role of friction. Expansion plays the role of the sliding motion. The payoff is immediate. Deceleration is expected, and it is expected to fade as density falls. Another slow visual anchor keeps the idea physical and non-abstract. In the cluster halo, the density is not uniform. It is layered. The inner region is bright and compact. The outer region is a faint envelope. The envelope has a gradient edge that blends into the filament. The gradient indicates how mass is distributed. Where the gradient is steep, gravity changes rapidly with position. Where the gradient is gentle, gravity changes slowly. Over time, matter drifts inward. The inner region becomes more concentrated. The outer region becomes more extended. This deepens the cluster's potential well. It strengthens the local gravitational field. Local fields pull galaxies into tighter orbits within the halo. Local fields also tug on nearby flows within filaments. This is not the whole expansion story, but it reveals the direction gravity prefers. It prefers gathering. It prefers tightening. That preference is the seed of breaking on the larger scales when averaged across everything. Another small understanding settles. The same process that builds clusters also suggests an overall tendency to slow expansion because building requires attraction. The step from local attraction to cosmic breaking uses an average. Expansion is not the motion of galaxies through a static space. It is the change in the scale of space itself between distant regions. Yet if the average density is high, the equations that relate density to expansion predict a stronger deceleration. The logic is quiet and consistent. More mass energy yields more curvature of space-time. More curvature yields more gravitational effect on expansion. The effect does not point outward. It points toward less rapid stretching. A scale shift carries the mind from halos to the whole sky. A single cluster spans a few million light-years. A filament can stretch for tens of millions. The separation between major knots can be hundreds of millions. Over such spans, the universe looks like a sparse lattice. Yet the average density across a very large volume still matters. The volume grows as expansion continues. Matter spreads thinner. Breaking should gradually weaken. This produces a particular curvature in the distance redshift relation. The curvature encodes deceleration. The expectation is therefore not arbitrary. It is linked to the observed growth of structure. If clusters grow and filaments tighten, matter must be doing work through gravity. That work costs kinetic expansion in a certain bookkeeping sense. Another small understanding settles. The growth of structure and the breaking of expansion are two sides of the same gravitational coin. A gentle limit of intuition appears here because the mind wants to picture a tug-of-war with two teams. Gravity is not a force pulling on expansion like a rope. Expansion is a property of the metric that defines distance at large scales. The connection between density and expansion is encoded in equations that do not resemble ordinary pushes. The limit is a modelling limit. The intuitive picture can mislead when it treats expansion like a projectile slowing under a force. The safer picture is the average behaviour of distances between distant regions. Those distances can slow in their growth rate when density is high. Another limit is observational. The average density is not measured directly everywhere. It is inferred from light and from structure. Some matter is dark and does not shine. The inferred density therefore has uncertainty. That uncertainty affects the inferred amount of deceleration expected in a matter-dominated model. The boundary is clear. A model can predict deceleration only as well as density is known. Another slow scene returns to the cluster edge, focusing on a boundary line that holds the concept. Along the halo's outer rim, the galaxy density drops. The drop is gradual. The rim is like a soft shoreline. Inside the shoreline, galaxies are frequent. Outside, they are sparse. Over time, the shoreline can drift outward as the halo grows. The growth indicates ongoing accumulation. Accumulation implies gravitational attraction continues to operate effectively. If attraction continues to operate, deceleration remains a natural baseline assumption for expansion. That baseline stands until evidence bends away from it. Another small understanding settles. The surprise of acceleration is stronger because the baseline of matter-driven deceleration is physically well motivated. A final scale shift ties the baseline to the supernova curve. Supernovae look back billions of years. Clusters look like slow sculptures that also build over billions of years. Both are shaped by the same cosmic parameters. If the supernova curve shows a late-time bend toward faster stretching, something must counter the expected breaking. The next checkpoint introduces a simple parameter. It describes how much mass energy exists per cosmic volume. That parameter sets the stage for what can dominate and when. A single curve can be guided by a simple quantity, how much matter exists per cosmic volume. That quantity density sets whether expansion slows forever or changes character later. At this distance, the universe appears as alternating regions of glow and darkness. A filament is a soft ribbon with a brighter spine. A void is a broad basin where the background deepens. The boundary between them is a gentle gradient, not a wall. Along that gradient, galaxy counts rise from rare to frequent. The rise is smooth, like mist thickening into fog. That smoothness matters because it suggests an average description is possible. The average ignores small clumps. It keeps the large-scale ledger. A small understanding settles early. The expansion history depends on the average density more than on any single cluster. Density is often expressed relative to a special value. Critical density is the density that makes space flat on average. The definition can stay short. Critical density is the boundary between open and closed curvature. The boundary is not a physical edge in space. It is a dividing line in model behaviour. If total density is above that line, gravity is stronger in the global budget. If total density is below it, gravity is weaker in the budget. The key payoff arrives quickly. Knowing density relative to this boundary tells whether matter alone can explain the observed distance curve. A calm analogy holds the concept without reusing earlier ones. Picture a wide bowl filled with syrup. Small bubbles rise slowly through it. If the syrup is thick, the bubbles rise sluggishly. If it is thin, they rise more quickly. The bubbles do not decide their speed. The medium sets the pace. In the cosmic case, expansion is the bubble motion. density is the syrup thickness. High density makes expansion slow more strongly. Low density makes expansion coast more easily. This analogy does not claim space is a fluid. It carries one controlled point. The global medium matters. A new visual anchor keeps the idea anchored to shapes and boundaries. A large spherical region is imagined in space not as an object but as a bookkeeping volume. Within that volume, matter is not uniform. It is concentrated in knots. It is stretched in filaments. It is sparse in voids. Yet the average across the whole sphere can be defined. The sphere's edge is an imaginary boundary. It cuts across filaments and voids equally. When the sphere is larger than the Webb scale, the average stabilizes. The stabilization is the practical goal. Another small understanding settles. Averaging over a sufficiently large region makes density a stable parameter, despite the Webb's patchiness. The next checkpoint is how density changes with time. Matter density declines as the universe expands. The decline is steep in the early universe. It becomes gentler later as the volume grows. Radiation declines even faster. Any component that does not decline much would eventually dominate. This is the quiet logic behind late-time surprises. It does not yet name the component. It only sets a stage where matter becomes less influential over time. A scale shift carries the mind from local knots to the whole cosmic budget. A single galaxy occupies a tiny fraction of a large volume. Even a rich cluster occupies a minute fraction. The dominant fraction is the empty void volume. Over billions of years, expansion increases that void volume. Matter remains in the same total amount, but it spreads thinner on average. The budget therefore changes its weighting. Another small understanding settles. A universe can be matter-dominated early, while becoming something else dominated late, because matter thins with expansion. A single number offers a foothold without demanding precision. The average matter fraction today is about 3/10 of the critical density. That is like 3 cups of water in a 10-cup container. It is not enough by itself to reach the flat boundary. In such a case, matter alone would predict an expansion that coasts or decelerates gently. It would not naturally create the observed late acceleration in the simplest framework. The payoff arrives in plain form. If matter contributes only a fraction of the critical density, an additional component is needed to match a flat geometry and the supernova curve together. Another slow scene keeps the geometry physical. In a broad void, the galaxy distribution is sparse. The few galaxies present appear as isolated points. Their halos are faint and rounded. Their edges fade into the background. Around the void rim, the filament brightens. The filament shows a sharpest change in density near its spine. That change is a gradient in mass distribution. The gradient shapes local gravity. Yet local gravity does not decide the global density budget. The budget is an average over many such gradients. The contrast between rim and center illustrates why intuition can fail. The eye is drawn to bright knots. The volume is dominated by darkness. A gentle limit of intuition appears and is made specific. Intuition tends to count objects rather than volume. A cluster looks important because it is bright and dense, but clusters occupy little volume. The average density is mostly set by the vast space between them. This is a limit of reasoning by visual prominence. Another limit is observational. Much of the matter does not emit light. It is inferred indirectly from gravitational effects and from structure growth patterns. The inference has uncertainty. That uncertainty propagates into the density estimate. The limit is clear. The density parameter is not read off from direct weighing. It is reconstructed from multiple lines of evidence. A calm scene helps the reconstruction feel tangible without introducing instruments. Light from background galaxies can be subtly distorted by the gravity of foreground mass. The distortions are faint arcs and slight stretches in the shapes of distant smudges. The arcs curve around cluster halos. Their curvature implies mass distribution. The halos show layered profiles. Stronger curvature near the core, weaker curvature in the outskirts. These profiles help estimate total matter content. Another small understanding settles. Even without seeing dark matter directly, its presence shapes the curvature of light paths and the growth of the web, which in turn constrain density. Once density is constrained, the expansion story becomes sharper. If matter fraction is below the flat boundary, curvature would be open unless another component fills the remainder. If curvature is near flat, another component is implied. If supernovae show acceleration, that component must also affect expansion in a specific way. The next step is therefore natural. It is to introduce a component that does not thin like matter. It can remain roughly constant per volume. Such behaviour would allow it to be negligible early and important late. The section ends with a soft transition. With density setting the baseline and matter thinning over time, the next section considers the simplest added component. It behaves like a constant background energy in empty space. The emptiest regions carry a quiet question: what remains when matter thins away? A simple model answers with a constant background energy that does not dilute as space expands. At this distance, a vast void opens between filaments. Its interior is a dark basin with only a few faint galaxies. The basin is not flat. It has a gentle depth in density. The centre is most rarefied. The rim shows a rising gradient where filaments begin. Along the rim, the glow of galaxies forms a soft, incomplete ring. The ring has thicker segments where the filament spine passes. It has thinner segments where the rim is weaker. The physical detail is a boundary gradient. It marks where matter gathers and where it does not. In the centre of the basin, nothing obvious pushes outward. Yet the distance between far filaments still grows with time. A small understanding settles early. If a component stays constant per volume, it becomes dominant as matter spreads thinner. This component is often linked to the vacuum itself. Vacuum energy is energy associated with empty space. The definition stays short. Vacuum energy is a persistent energy density of empty space. The phrase can sound abstract, but its effect is simple in the equations. Matter density drops as the universe expands. Vacuum energy does not drop. Over time, a non-dropping term becomes relatively more important. Then the expansion curve bends toward acceleration. The next payoff arrives quietly. A constant term can explain why acceleration appears late, not early. A calm analogy holds the idea without repeating earlier images. Imagine a wide plain with a very light wind that never changes. At first, a heavy fog fills the plain. The wind barely moves the fog. As the fog thins, the same wind becomes more effective. The wind does not strengthen. The environment changes. In the cosmic case, the fog is matter density. The wind is the constant term. When matter is dense, gravity dominates and expansion decelerates. When matter is sparse, the constant term becomes noticeable, and the expansion accelerates. The analogy does not claim space has wind. It keeps one controlled relationship. A constant influence can matter more when other influences fade. A new visual anchor keeps the constant term tied to space itself. In a deep void, the background darkness looks smooth. The few galaxies present have faint halos with soft edges. Between them there is no obvious structure. The emptiness feels uniform. In that uniform region, a constant energy density would be uniform too. It would not clump into knots. It would not form filaments. It would remain spread evenly. The image is of a quiet, even pressure that fills a container regardless of how the container grows. Another small understanding settles. The constant model predicts uniformity, which matches the idea that dark energy does not gather into visible structures. The constant model is often named the cosmological constant. Cosmological constant is a constant energy density term in gravity. The definition stays short. Cosmological constant is a constant term in the expansion equations. It acts like a negative pressure in the bookkeeping of expansion. The phrase negative pressure can be kept gentle. Pressure is how energy responds to volume changes. In this model, the effective pressure is such that expansion is encouraged rather than resisted. The mechanism does not require a force pushing outward in space. It alters how the expansion rate responds to energy content. Another payoff arrives. Acceleration can arise from how energy scales with volume, not from any local shove. A slow scene of motion and layering keeps the idea physical. Consider a filament edge where density drops into a void. The filament has a brighter spine. Around the spine, a sheath of lower density surrounds it. The sheath fades into the basin. Over time, the basin's volume grows. The filament remains as a narrow structure while the basin expands around it. The boundary gradient becomes broader. The sheath becomes more extended. Matter within the filament continues to attract locally. Yet the average space between far filaments grows faster once the constant term dominates. The result is a growing isolation of structures. Another small understanding settles. The constant model predicts that large-scale separations grow faster, while local bound structures remain intact. A single number gives the constant model a recognizable share. The constant term is often associated with about 7/10 of the critical density. That is like 7 cups in a 10-cup container. Combined with matter at about 3/10, the total sits near the flat boundary. This number is not a decorative detail. It explains why geometry can be near flat while matter alone is not enough. It also explains why acceleration appears at late times. The constant term is present early, but matter is then dominant. Later matter thins and the constant term takes over. A scale shift carries the mind from void boundaries to cosmic time. In the early universe, the average density is far higher. A constant term is then a small fraction of the total. In the late universe, the average density becomes low. A constant term then becomes a large fraction. Over billions of years, dominance changes hands. That change reshapes the distance redshift curve seen in supernova. It also reshapes the growth rate of the cosmic web. Filaments keep forming, but their growth slows as acceleration begins. Another payoff settles. The constant model links 3 observations with one simple behavior, a term that does not dilute. Now, a limit of understanding arrives, and it is specific. The constant model fits data well, but it does not explain why the constant has its particular value. If vacuum energy is associated with quantum fluctuations, simple estimates can overshoot wildly compared to the inferred density. The limit is theoretical. There is no widely accepted mechanism that sets the constant to the observed small scale. Another limit is observational. A constant model predicts a particular detailed shape for the expansion curve. Alternative models can mimic it closely over the observed range. The limit is degeneracy. Different equations of state can produce nearly the same distance redshift relation when data are finite and noisy. This is why multiple probes are needed. Structure growth and early universe constraints help break the tie. A slow scene returns to the void ring to keep the debate grounded. The rim brightens in a few arcs. The arcs mark where matter gathers. The basin remains smooth. The overall picture suggests a universe where emptiness dominates volume. In such a universe, a uniform term can quietly govern the late-time expansion. The constant model offers a calm, minimal answer. It adds one term and explains the bend in the curve. The next step is to consider a less rigid possibility. The next section follows a model where the dark energy density can drift with time, like a field that changes slowly across cosmic epochs. A constant can fit the curve, yet the universe also allows the possibility of a slow drift instead. In that possibility, dark energy behaves like a field whose strength changes gently across time. At this distance, a wide filament stretches across the scene like a pale ribbon. Its spine is brighter. Its flanks taper into emptiness through a smooth gradient. Near the spine, small groups of galaxies form bead-like knots. Between knots, the ribbon narrows and then widens again. The widening and narrowing suggest that matter flows along the filament over long times. Beyond the filament, a void opens with a dark, almost uniform floor. The floor is not perfectly uniform. It holds a faint gradient where the filament's influence fades. This is a useful stage for a different idea. A field can vary in value without forming sharp edges. It can change slowly across space and across time. A small understanding settles early. If dark energy is a field, it can imitate a constant while still evolving. This model is often called quintessence. Quintessence is a slowly changing scalar field energy. The definition stays short. Quintessence is a field whose energy density evolves with time. The appeal is gentle. A constant demands one fixed value forever. A field allows a value that was different in the past. The distance redshift curve then becomes a record of that change. The curve can remain close to the constant case over the observed range. It can also deviate slightly. Those deviations may appear in subtle shifts in the supernova curve and in structure growth. Another small understanding settles. A drifting field can match acceleration while leaving a small imprint that a perfect constant would not. A calm analogy keeps the drift intuitive without borrowing earlier images. Imagine a long shoreline at night with a tide that is changing. The tide is never violent. It rises or falls in a slow, steady way. At 1 hour, the waterline rests at one mark. At a later hour, the waterline rests at another. The rocks do not move. The sea level changes. In the cosmic model, the sea level is the field's energy density. The shoreline marks the transition where the field becomes dynamically important. The analogy holds one point. A gradual change can accumulate into a clear difference over time. A new visual anchor brings the field into a slow physical picture. Across a deep void, faint background glow is nearly uniform. Over that uniform darkness, imagine an invisible potential landscape. The landscape is not hills of matter. It is a gentle slope in a field value. The slope is extremely shallow. Over huge distances, the field value shifts slightly. Over huge times, the field can roll along that slope. The rolling changes how much energy is stored in the field. The change then alters the expansion rate. The physical detail is a gradient, but not in matter. It is a gradient in a field that permeates space. Another small understanding settles. In a field model, acceleration is linked to how slowly the field rolls, not to a fixed constant. The next checkpoint is how such a field produces effective pressure. Pressure is how energy changes with volume. In a rolling field, part of the energy is like potential energy. Part is like kinetic energy of change. If the field changes very slowly, the potential part dominates. In that regime, the effective pressure is strongly negative and acceleration occurs. If the field changes faster, the kinetic part grows. The effective pressure becomes less negative. Acceleration weakens. This gives the model a dial. The dial is how fast the field evolves. Another small understanding settles. The same field can behave nearly constant at one epoch and less constant at another depending on its roll speed. A slow scene of layers keeps the idea grounded in time. Consider a line of supernovae at increasing redshift. Each is a faint bloom within a smudge of a host galaxy. Their peaks are corrected. Their redshifts are measured. The curve they trace is smooth. In a constant model, the curve has one fixed bend shape. In a field model, the bend can be slightly different. The difference is not a jagged feature. It is a gentle change in curvature spread over many redshifts. The physical picture is like a long arc drawn with a flexible strip. One strip is perfectly uniform. Another has a slightly variable stiffness along its length. Both create smooth arcs, but not identical ones. Another small understanding settles. The signature of a field is not a dramatic departure, but a small systematic change in the arc of the expansion history. A single number offers a foothold without heavy notation. In many field scenarios, noticeable changes are constrained to be small since redshift about 1. That is like looking back roughly 8 billion years. The curve from that era to now is already well tested. Large departures would have been obvious. The allowed drift is therefore gentle. This is important. It keeps the model from becoming a loose story. It must remain close to the observed curve. The payoff arrives. A field model is flexible, but not free. Data restrict how much it can change in the recent universe. A scale shift carries the mind from a void gradient to cosmic age. On small scales, a field value appears uniform. It cannot be sensed locally without a coupling. On cosmic scales, its average value affects expansion. Over billions of years, even a tiny drift can change the balance between matter and dark energy. That balance shapes how voids widen and how filaments grow. In a constant model, growth slows in a particular way. In a field model, the slowdown can have a different timing. Another small understanding settles. Structure growth provides an additional test because it responds to the same expansion history the field controls. Now, a limit of observation appears and is made specific. Supernova distances and redshifts mainly test the integrated expansion. Many different histories can integrate to nearly the same curve over a limited redshift range. This is a degeneracy limit. It means distance data alone can struggle to separate a constant from a gently evolving field. Another observational limit appears in structure growth. The web is measured through galaxy distribution, and galaxies trace matter imperfectly. The mapping from galaxies to total mass carries uncertainty. That uncertainty limits how sharply growth can distinguish models. The limit is clear. Even if the field drifts, the drift can hide within measurement scatter and within the galaxy mass relation. A gentle conceptual limit also appears. A field is a mathematical object, not a visible substance. Its properties are inferred from expansion and growth. This inference is indirect. It can fit many shapes if not constrained. Constraints must therefore be tied to multiple probes. A slow visual anchor returns to the void floor and rim. The rim brightens where filaments meet. The floor remains smooth and dark. The expansion continues to widen the basin. If the dark energy is a field, the basin widening rate could change slightly with time. The change would be quiet. It would show as a subtle difference in the distance curve and in how quickly the rim structures sharpen. The section ends with a soft handoff. If a field can change, then gravity itself might be questioned as well. The next section considers models where the law of gravity changes on large scales, producing acceleration without adding a new energy component. A curve that suggests acceleration can be explained by new energy, yet it can also be explained by new gravity. In that alternative, the law that links mass to cosmic expansion changes on the largest scales. At this distance, a massive cluster sits at the junction of several filaments. The cluster core is bright and dense. Its outer halo is a wide envelope with a soft boundary. Around the halo, faint arcs of distorted background light appear as thin crescents. The crescents curve smoothly around the cluster. Their curvature is strongest near the dense core. It weakens toward the halo edge. The edge itself is a gradient where the halo fades into the filament. This scene contains a quiet truth. Gravity shapes both the growth of structure and the path of light. If the law of gravity changes, both of these may change together. A small understanding settles early. Modified gravity models aim to change expansion without adding dark energy. Modified gravity is a change to how gravity behaves on large scales. The definition stays short. Modified gravity is gravity that differs from general relativity at large scales. The motivation is not dramatic. It is economical. If acceleration is a symptom of a missing term in the equations, the term might belong to gravity itself. A familiar analogy holds the idea without repeating earlier ones. Consider a long river whose flow is governed by a set of channels and gates. If the gate rules change downstream, the same upstream water can produce a different water level pattern. The water is not new, the rules of flow differ. In the cosmic case, matter is the water. Expansion is the downstream water level pattern. Gravity is the gate rule set. Changing the rule can change the global pattern without adding a new substance. The payoff is immediate. Acceleration can arise from altered rules rather than extra contents. A new visual anchor keeps the altered rules tied to physical detail. Along one filament, a thin sheath of matter extends beyond the visible galaxy spine. The sheath is inferred from how light bends. The bending pattern suggests the mass distribution. In standard gravity, the bending and the growth of structure are linked by the same law. In some modified gravity models, the link changes. Light bending can respond to one effective potential. The motion of matter can respond to another. The difference can be small. It can still matter across cosmic distances. The physical picture is of two layered influences. One shapes the curvature of light paths. Another shapes the clustering of matter. If they separate, the universe offers a test. Another small understanding settles. Comparing lensing to structure growth can reveal whether gravity follows the standard rule everywhere. Many modified gravity ideas introduce a mechanism that hides changes in dense regions. The hiding is needed because gravity works well in galaxies and clusters. Changes must appear mainly in low-density environments or on very large scales. Screening is a mechanism that suppresses modified gravity in dense regions. The definition stays short. Screening is a way modified gravity turns off where matter is dense. This creates a visual consequence. Inside a cluster core, gravity behaves normally. At the halo boundary where density drops, modifications can begin to appear. The boundary becomes more than a mere fade. It becomes a transition zone in the law itself. Another payoff arrives. Low-density voids and halo edges become the natural laboratories for testing modified gravity, because screening is weakest there. A slow scene moves into a void adjacent to the filament. The void interior is dark and smooth. The filament edge shows a gradual density gradient. In standard gravity, matter in the filament slowly pulls on the void edge. It causes a gentle flow outward from the void and inward toward the filament spine. In modified gravity, that flow can be faster or slower depending on the model. If the effective gravitational strength is enhanced in low density, voids can evacuate more efficiently. Their interiors can become emptier. Their boundaries can sharpen. If the strength is weakened, the opposite occurs. The void looks less carved. The boundary looks softer. Another small understanding settles. The same supernova curve that implies acceleration can be accompanied by distinctive changes in how voids and filaments evolve. A scale shift carries the mind from the cluster arcs to the universe-wide pattern. A single arc is a local trace of curvature. A web of arcs across the sky would map the large-scale distribution of mass. Over billions of years, that mass distribution grows from small fluctuations into the web. Gravity controls the growth rate. Expansion controls how quickly matter can respond. In standard dark energy models, acceleration slows growth mainly by increasing the expansion rate. In modified gravity, growth can be altered directly by changing the gravitational response. This creates a separate handle. Distance data constrain expansion history. Growth data constrain the strength of clustering. If the two handles disagree under standard gravity, modified gravity becomes tempting. Another small understanding settles. The test is not only whether distances fit a curve, but whether growth matches the same curve under one consistent gravity law. A single number offers a foothold without forcing precision. Many modified gravity effects are designed to appear only beyond about 100 million light-years. That is like spanning the width of a large cosmic void. Below that scale, screening keeps gravity close to its familiar form. Above that scale, the changes can accumulate and affect the expansion curve. The number matters because it directs where differences should be sought. It also carries a scale shift. A galaxy is small compared to that threshold. A filament segment can be comparable. A web scale pattern can exceed it. Another payoff arrives. If changes only emerge beyond a certain scale, the smoothest regions and the widest separations become the key places to look. A limit of observation enters, and it is specific. Modified gravity predictions often depend on subtle differences between lensing and motion. Lensing measures how light paths bend. Motion measures how matter clusters and streams. Both are inferred from faint patterns. Those patterns can be blurred by projection. They can be contaminated by complex mass distributions along the line of sight. The limit is the ability to separate three-dimensional structure from two-dimensional projection. A second limit is modeling. Baryonic matter can reshape mass profiles within halos. Gas physics can mimic or hide small changes in gravity. This complicates interpretation of halo boundaries and void shapes. The boundary is clear. Even if gravity changes, ordinary astrophysical processes can create similar signatures in some observables. A gentle conceptual limit also appears. Modified gravity must remain stable and consistent across cosmic time. It must not break early universe constraints. It must not create contradictions in well-tested regimes. These requirements narrow the space of plausible models. The section returns to the crescent arcs around the cluster. The arcs are smooth and quiet. They suggest an ordered bending field. At the halo edge, the curvature weakens. The filaments extend beyond, and the void opens beside them. This arrangement offers a natural progression. From dense core to halo boundary to void interior, the environment changes from screened to unscreened in many models. The next checkpoint is therefore the limits of measurement that decide between these stories. The following section follows how uncertainty blending and cosmic scatter constrain the conclusions drawn from all these curves and patterns. The story of acceleration is not limited by imagination, it is limited by scatter. The evidence strengthens when uncertainty is understood and contained rather than ignored. At this distance, a supernova appears as a faint point within a dim host galaxy. The host is a soft oval with a brighter core and a fading edge. The supernova sits slightly off-center near a spiral-like arm that is only barely visible as a streak of light. Around the point, the background is uneven. It has a gradient of glow from the host core outward. That gradient makes the peak measurement delicate. The point must be separated from the glow beneath it. A small understanding settles early. The expansion curve is extracted from many imperfect measurements, and the imperfections have patterns. One pattern is intrinsic scatter. Even corrected supernovae are not perfectly identical. Their peak brightness varies slightly. Their color evolution varies slightly. Their decline shape varies slightly. These variations are small, but they matter when comparing faint points across billions of years. Another pattern is environmental. A supernova in a dusty region can be dimmed and reddened. A supernova in a cleaner region can look brighter. Dust correction helps, but it can leave residuals. The residuals can be correlated with host type. Another small understanding settles. The key is not eliminating scatter, but modelling it so the mean curve remains trustworthy. A calm analogy keeps this method in a familiar frame without repeating earlier images. Consider a set of identical bells hung along a long path. Each bell should sound with the same loudness. A breeze and nearby foliage can muffle some bells more than others. The listener can still infer distance from loudness if many bells are heard. The listener must also learn how the muffling behaves. Some muffling depends on wind direction, some depends on foliage density. In the cosmic case, supernovae are the bells. Dust and lensing are the mufflers. The payoff arrives. A population can reveal a trend even when each member is imperfect, provided the imperfections are understood. A new visual anchor keeps the sense of population and scatter concrete. Across a wide field, dozens of host galaxies form a sparse pattern. In some, a supernova has occurred. Each event has a light curve that rises and falls. Each event has a measured redshift. Each event yields a distance estimate with an error bar in the mind, even if not drawn. When plotted conceptually, these points form a band. The band has thickness. It is not a line. Some points lie above the mean curve, some lie below. The mean curve is the target. The thickness is the scatter. Another small understanding settles. The thickness of the band is a measurable quantity that sets how many events are needed to distinguish curves. One source of thickness is weak lensing. Mass along the line of sight can slightly magnify or demagnify a distant supernova. The effect is small for most lines of sight. It grows in importance at higher redshift. It creates a skew. Most lines are near average. A few are more strongly magnified or demagnified. The physical detail is a subtle stretching of background galaxy shapes, into faint arcs and ellipses. Those distortions trace the same mass that lenses supernova light. Another small understanding settles. Lensing adds scatter, but not a systematic dimming that mimics acceleration across many independent sightlines. Another source of thickness is selection. Faint events are harder to include. If only the brighter examples at a given redshift enter a sample, the mean can be biased. This is a limit of observation, and it is specific. The limit is detection threshold and background confusion. Host galaxy light can drown a supernova near the core. Sky background can swallow faint points. This can remove some events preferentially. Correcting for this requires careful accounting. Another limit is calibration. The brightness scale must be consistent across the dataset. Small offsets in calibration can shift the inferred curve. These offsets can depend on wavelength band and on redshift, because redshift moves features through bands. The boundary is clear. Even a small calibration drift can masquerade as a change in the expansion curve if it correlates with redshift. A scale shift arrives with one calm number. A typical corrected supernova distance precision per event is about 7%. That is like estimating the length of a long hallway and being off by 7 steps out of 100. For a single event, that uncertainty is large compared to the subtle bend in the curve. For 100 events, the mean uncertainty shrinks. The shrink is not magical. It is the square root behavior of averaging. The payoff arrives. Large samples turn noisy individual candles into a precise mean curve. Another slow scene keeps the calibration idea tied to physical detail. The supernova spectrum has absorption notches that shift with redshift. The notches slide into different wavelength regions. As they slide, the observed light in a fixed band samples different parts of the spectrum. If the band response is not perfectly known, the inferred brightness can shift slightly with redshift. This is a specific limit. It is a limit of band-pass knowledge and spectral correction. The correction relies on models of supernova spectra. Those models have uncertainty. Yet the models are constrained by nearer events with better data. This creates a ladder of inference. Each rung adds uncertainty but also adds a cross-check. Another small understanding settles. The strength of the evidence comes from internal consistency checks, not from any single measurement. Another calm analogy helps without repeating earlier ones. Imagine measuring the depth of a lake by dropping stones and listening for splashes. Different stones fall differently. Wind changes sound. Some drops are muffled by reeds. One drop tells little. Many drops at many points map the depth pattern. The pattern emerges despite noise. In the cosmic case, different methods act like different stones. Supernovae measure distances. Lensing measures mass distribution. The cosmic web measures growth. When they converge, confidence rises. Now a limit of intuition appears gently and clearly. Intuition wants a single decisive graph that proves acceleration. Real inference is layered. It depends on priors about dust lensing and population evolution. It depends on modelling systematics. This is not a weakness. It is the actual texture of empirical cosmology. The boundary is that no observation is free of assumptions. The goal is to use many observations so that assumptions can be tested against each other. Another small understanding settles. The most persuasive result is not one clean data set, but a network of constraints that are hard to satisfy simultaneously under a wrong model. The section ends with a soft transition. Once uncertainty is treated as part of the signal, the next step is to bring in a different early universe anchor. That anchor is an imprint from a time when the universe is far younger. It provides a scale that can be compared to the late-time expansion curve. A late-time curve becomes clearer when it's paired with an early-time ruler. That ruler is an ancient pattern that sets a standard length across the universe. At this distance, the scene is not a galaxy or a cluster. It is a nearly uniform darkness, with a faint grain like a fine dusting across a black surface. The grain is not random. It has slightly brighter flecks and slightly dimmer hollows. The differences are tiny. They form a mottled texture with no sharp edges. Over large angles, the texture looks smooth. Over smaller angles, the texture shows a gentle speckle. This is a picture of a very early imprint carried by light. A small understanding settles early. The early universe leaves a preferred scale that can be used as a measuring stick. That stick is often called the sound horizon. Sound horizon is the distance sound waves travel in the early plasma. The definition stays short. Sound horizon is the maximum distance early pressure waves can reach, before atoms form matter and light are tightly coupled. Pressure waves travel through that hot mixture. They create alternating regions of slightly higher and lower density. When the universe cools enough for atoms to form, light decouples and streams freely. The wave pattern freezes into the distribution of matter and into the background light texture. The payoff arrives quietly. A scale set in the early universe can be recognized later as a preferred separation in the cosmic web. A calm analogy holds this without repeating earlier ones. Imagine ripples spreading across a calm pond after a single gentle tap. The ripples travel outward. After a while, the pond surface suddenly freezes into ice. The ripple spacing becomes locked into the ice pattern. Much later, cracks in the ice still show that spacing. The water is gone from view, but the spacing remains. In the cosmic case, the pond is the early plasma. The ripples are sound waves. The freezing is recombination when atoms form and light decouples. The cracks are the later matter distribution that carries the same preferred scale. Another small understanding settles. The ruler is not built in the late universe. It is inherited from an early epoch and carried forward by expansion. A new visual anchor keeps the ruler tied to physical detail. In the galaxy distribution, a faint ring-like excess can be imagined around a typical overdense region. The ring is not a literal circle in the sky. It is a statistical shell in 3 dimensions. Around each dense knot, there is a slightly higher chance of finding another knot at the sound horizon separation. The physical detail is a shell boundary. It is diffuse and broad. It is not sharp, yet it is consistent across the universe. This shell is what baryon acoustic oscillations encode. Baryon acoustic oscillations are the leftover sound wave imprint in matter. The definition stays short. Baryon acoustic oscillations are a preferred separation scale in galaxy clustering. The payoff comes in plane form. If the ruler length is known from early physics, its apparent size at different redshifts reveals the expansion history. A scale shift carries the mind from tiny temperature flex to enormous distances. In the early universe, the sound horizon is set when the universe is only hundreds of thousands of years old. In the late universe, the same scale is traced by galaxy, clustering across billions of light years. The leap is enormous. A pattern born in a young hot universe becomes a ruler for a mature cold universe. A single number can be used as a foothold. The sound horizon is about 500 million light years. That is like spanning a distance so large that a galaxy cluster becomes a speck by comparison. This number is not used to impress. It is used to anchor scale. When the ruler is seen at different epochs, its apparent angle and redshift separation change according to the expansion rate. Another small understanding settles. Supernovae provide a distance ladder based on standard candles, while the sound horizon provides a standard ruler based on early physics. Together they cross-check the same expansion history. A slow scene returns to the faint grain of the early background. The grain has a characteristic smoothness. It is not clumped like the late web. It is almost uniform with only slight differences. Those slight differences carry the seed pattern. As time passes, gravity amplifies the seeds. Dense seeds become filaments and clusters. Sparse seeds become voids. Yet the preferred separation scale remains embedded. It becomes visible statistically as a bump in the correlation of galaxies. The bump is subtle. It is spread out. It is not a sharp peak. This is a limit of observation, and it is specific. The limit is cosmic variance and survey volume. Because the ruler is so large, only a finite number of independent regions fit within the observable universe. This limits how precisely the feature can be measured. Another observational limit is tracing bias. Galaxies are not the mass itself. Their distribution can be biased relative to total matter. The bias must be modelled to extract the ruler signal. Another limit is non-linear growth. Over time, gravitational clustering smears the feature. Random motions of galaxies within halos blur the precise separation. The feature becomes broader. This broadening must be accounted for. The boundary is clear. The ruler is not painted on a pristine canvas. It is carried through billions of years of gravitational evolution that can distort and soften it. Another small understanding settles. The ruler is robust because it is anchored in early physics, yet it requires careful handling because late-time structure growth blurs it. A calm analogy supports this handling without repeating earlier images. Consider a pattern pressed into soft clay with a stamp. Later the clay is gently kneaded. The pattern is still present, but edges soften. The stamp size remains. The pattern is less crisp. The size can still be recovered by looking at the average spacing of grooves. In the cosmic case, early physics stamps a ruler. Late structure formation needs it. Recovery relies on statistical averaging across many regions. Another payoff arrives. When supernovae, the ruler and growth constraints agree on a late-time acceleration, the conclusion becomes harder to dismiss as a single systematic. Yet this convergence also highlights remaining tensions. If early and late measurements of expansion disagree in detail, the model may need refinement. The section ends with a soft transition. With an early universe ruler now in place, the next section widens the view to the full expansion history and its implications. It considers how acceleration shapes the far future and the large-scale fate of the cosmic web. A universe that accelerates reshapes distance first, then it reshapes connection. The long-term effect is a slow thinning of the cosmic web as separations grow faster than structure can reach. At this distance, the web looks like a lacework of pale filaments. Each filament has a bright spine and a softer halo. Between filaments, voids open like dark bays. The bays have smooth interiors and rim gradients that rise toward the filaments. The rims are not uniform. They show thicker arcs where multiple strands meet. They show thinner stretches where the rim relaxes. This physical geometry matters. Acceleration does not tear structures apart locally. It changes how easily structures can influence each other across great gaps. A small understanding settles early. Acceleration makes co-moving distances grow, but bound structures remain bound. Co-moving distance is distance measured with expansion factored out. The definition stays short. Co-moving distance is distance scaled to remove overall expansion. The concept helps describe the web's evolution. In comoving coordinates, galaxies in a cluster stay near each other. In physical coordinates, the space between far clusters grows faster with time. This distinction prevents a common confusion. A cluster does not dissolve because the universe expands. The cluster is held by gravity. The accelerating expansion mostly appears between clusters, across voids, and along the vast separations of the web. Another small understanding settles. Acceleration changes the background stage on which gravity acts, rather than acting like a local wind pushing matter away. A calm analogy holds this without repeating earlier ones. Imagine a slow conveyor belt beneath a set of magnets placed on a table. Each magnet holds a small pile of iron filings tightly. The conveyor belt carries the table surface beneath them, stretching the spacing between piles on the belt scale. The piles themselves stay coherent. Only the gaps between piles widen over time. The analogy keeps one point. Local binding can coexist with global separation. A new visual anchor turns the long-term effect into a clear scene. Far across a void, two filament walls face each other. Each wall is a sheet of faint galaxies. The sheets are not perfectly flat. They have gentle folds and thickness. They define the void boundary. The interior remains dark and smooth. Over time, the void expands. Its diameter increases. The sheets recede from each other in physical space. Their edges become more isolated. The matter within each wall continues to settle and merge locally, but the chance of new bridges forming across the void diminishes. The payoff arrives. Acceleration gradually locks the web into separate islands of structure by widening the emptier spaces fastest. Another checkpoint moves from geometry to horizons. In an accelerating universe, there can be an event horizon. Event horizon is a distance beyond which signals never arrive. The definition stays short. Event horizon is a limit beyond which light cannot reach an observer. This is not the horizon of a black hole. It is a horizon of cosmic expansion. Light emitted from beyond a certain distance can be stretched so strongly by expansion that it never crosses the growing gap. The existence and scale of this horizon depend on the expansion history. It is one way to describe how acceleration affects causal contact. Another small understanding settles. Acceleration can create a boundary of reach, not by blocking light, but by making the space between grow too quickly. A single number provides a soft foothold. In a model close to a constant dominated future, the event horizon scale is on the order of tens of billions of light years. That is like a boundary so large that the local supercluster is a small patch within it. The number is rounded because the idea is more important than the exact value. It carries an everyday comparison. It is like standing in a fogless plain where the farthest visible ridge is fixed no matter how long the walk continues. The ridge is not closer or farther in an absolute sense. The relation changes because the ground itself stretches. Another payoff arrives. A horizon makes the future universe not only emptier, but also more separated in what can ever be observed. A scale shift then settles into time. On the timescale of a human breath, expansion is imperceptible. On the timescale of a star's life, it is still subtle. On the timescale of billions of years, it reshapes the map. Filaments thin, voids grow. The contrast between dense knots and empty basins increases. The web becomes a set of brighter nodes connected by fainter and more elongated strands. In the far future, under a constant-like behavior, even the strands can fade in prominence compared to the growing void volume. Another small understanding settles. Acceleration changes the balance between surface area and volume, in the web making void volume dominate even more strongly. Now a limit of observation arrives, and it is specific. The future described here is extrapolated from a model fitted to a limited time window. The window is a small fraction of cosmic history. It is also a tiny fraction of the time over which the asymptotic behavior matters. This is a limit of inference. It rests on assuming that the dark energy behavior remains similar. If dark energy evolves or if gravity changes, the far future can differ. Another observational limit is that horizons and far future separations cannot be measured directly. They are derived from fitted expansion parameters. The parameters themselves depend on systematics and on model choice. The boundary is clear. The far future is model-dependent even when the present evidence for acceleration is strong. A gentle scene returns to the filament wall and void interior. The wall has a textured thickness. It is layered. The interior has a smooth darkness. At the boundary, faint galaxies trace a curve. The curve becomes slightly more stretched with time. The stretching is not dramatic. It is steady. It suggests a long drift toward isolation rather than a sudden break. Another payoff settles. Acceleration does not end the web. It quiets its connectivity. It makes the universe's large-scale structure more like separated archipelagos in an expanding ocean of emptiness. The section ends with a soft transition. Once the future shape is sketched, the next step is to return to the present and ask how competing models can be distinguished more sharply. The following section follows the specific signatures that could separate a true constant from a slow field or modified gravity using multiple observational handles together. A model is not chosen by elegance, it is chosen by fingerprints. The best separation comes when different observables are forced to agree on one story. At this distance, a wide patch of sky holds a quiet overlap. A sparse field of galaxies lies across a darker background. The galaxies form faint threads. Across the same region, background light from even farther sources is subtly sheared. The shear is not seen as motion. It is seen as a preferred stretch direction in many tiny shapes. Some shapes are slightly elongated tangentially around mass concentrations. Other shapes show a weaker alignment along filaments. The pattern is like a soft combing of the sky. It hints at the invisible mass distribution. A small understanding settles early. Distances, growth and lensing together can separate dark energy from modified gravity. The first concept is equation of state. Equation of state is the relation between pressure and energy density. The definition stays short. Equation of state is how pressure compares to energy density. In a constant-like model, the equation of state stays near -1. In a slowly evolving field, it can drift with time. This drift affects the expansion rate. It also affects the growth of structure by changing the background expansion. The second concept is growth rate. Growth rate is how quickly density contrasts increase with time. The definition stays short. Growth rate is how fast cosmic structure becomes more clumped. Modified gravity can change growth directly. A field like dark energy mostly changes growth indirectly through expansion. This difference creates a path to separation. The payoff arrives. If expansion looks the same under two models, growth can still differ, and lensing can expose it. A calm analogy holds the three handles together without repeating earlier ones. Consider a long piece of fabric being stretched on a frame. The stretch sets the overall spacing of the weave. That is like the expansion history. Now consider how a pattern of wrinkles grows or smooths as the fabric is stretched. That is like structure growth. Finally, consider how light reflects off the fabric surface. Reflection reveals hidden ridges and folds even when the weave looks uniform. That is like lensing, which responds to total mass distribution. If the fabric is made of a different material, the same stretch can produce different wrinkles and different reflections. Material differences are like changes in gravity or dark energy behavior. Another payoff settles. Matching only the stretch is not enough. The material properties must match the wrinkles and reflections as well. A new visual anchor focuses on the lensing pattern as a concrete fingerprint. Along a filament background, galaxies show a faint alignment that follows the filament spine. The alignment is strongest near nodes. It fades along the filament length. The physical detail is a gradient of shear strength. At one node, the shear forms a shallow ring-like pattern around a dense core. The ring is not sharp. It is a smooth annulus of slightly stronger tangential alignment. This ring traces a projected mass profile. If gravity is modified, the relation between this lensing profile and the motions that build the node can change. Another small understanding settles. Lensing is sensitive to the curvature of light paths. Growth is sensitive to how matter responds. Comparing them tests whether one consistent gravity law fits both. The next checkpoint is how expansion information enters. Supernova distances provide one curve. The early universe ruler provides another. Together they constrain the expansion rate at multiple epochs. If the equation of state drifts, the curvature of the distance relation with redshift changes subtly. The effect is gentle. It is not a dramatic kink. It is a small change in slope across time. Detecting it requires many measurements and careful control of systematics. A single number provides a foothold. Distinguishing a constant-like behavior from a mild drift often demands distance precision at about the 1% level across redshift bins. That is like measuring the length of a long hallway and being off by only one step out of 100. This is hard. It is not impossible. It is the scale of ambition in future surveys. The payoff arrives. The discrimination between models is limited less by imagination than by the precision flaw of measurements and calibration. A scale shift then settles into a quiet comparison across epochs. The early universe imprint is set when the universe is very young. The late universe acceleration is measured when the universe is mature. The models must connect these two eras smoothly. If a model fixes late time distances but fails to predict early universe constraints, it is weakened. If a model fits early constraints but predicts the wrong growth history, it is weakened. The combination is powerful because it spans time, it spans physical regimes, it spans different physical processes. Another small understanding settles. A successful model is one that fits the entire arc from early acoustic patterns to late cosmic web evolution with minimal tension. Now a limit of observation appears, and it is specific. Many discriminants rely on subtle differences in how lensing responds compared to galaxy clustering. These differences can be masked by baryonic physics within halos. Gas cooling and feedback can reshape inner mass profiles. That reshaping can mimic a small change in lensing signals on certain scales. Another limit is photometric redshift uncertainty in large surveys. If redshift estimates are blurred, the inferred growth and lensing tomography becomes less sharp. The limit is the width of redshift bins and the mixing between them. Another limit is modelling degeneracy. A changing equation of state can be partially traded against changes in matter density. A modified gravity parameter can be partially traded against neutrino mass. The boundary is clear. The inference lives in a multidimensional space where different effects can imitate each other within error bars. This does not erase the goal. It clarifies the need for multiple independent handles. Another calm scene returns to the filament with the shear gradient. The filament has a soft, luminous spine. The shear pattern is a ghostly alignment overlaid on faint points. Nodes show a thicker ring-like shear. Voids show weaker and more random orientations. Over time, more data tighten these patterns. The mean trends become clearer. Residuals become the focus. Residuals are where fingerprints hide. Another payoff settles. The future of this question is not one decisive observation, but many overlapping maps that must all align under one theory. The section ends with a soft transition. With the discriminants laid out, the final section can step back and let the whole arc settle. It moves from evidence and models to a quiet synthesis. It offers a stable picture of acceleration that can rest without suspense. The evidence for acceleration settles into place the way a long exposure settles into clarity. It does not arrive as a single flash. It accumulates as many faint points align into one curve. At this distance, the scene is simple and wide. A deep black field holds scattered galaxies. Some are sharp knots, some are smudged ovals. Across the darkness, a thin mist of background light forms a nearly uniform glow. Over it all, the large-scale pattern is quiet. It is a web with filaments and voids. It is a geometry that changes slowly. The early anchor is plain. Acceleration is inferred because distant standard candles appear dimmer than expected in a decelerating universe. That inference is strengthened because independent distance rulers and structure maps agree on a similar expansion history. The story is not about a single data set. It is about consistency across very different phenomena. The first concept returns in its calmest form. Expansion history is the record of how scale changes with time. The definition stays short. Expansion history is how cosmic distances grow as time passes. This record is not read by watching objects move. It is read by comparing brightness and size across redshift. It is read by noticing how a pattern imprinted early appears at a different angular scale later. It is read by the way structure grows from small ripples into a web. Another small understanding settles. Acceleration is not seen directly as a push. It is seen as the best explanation for a family of gentle mismatches that become one match under an accelerating model. A steady analogy holds the whole arc without repeating earlier ones. Imagine a shoreline traced by many tides over years. Each tide leaves a faint line of shells and sand. One line is messy. Many lines together reveal a stable slope and curvature. The slope is like the expansion rate at a given era. The curvature is like the change of that rate with time. A single walk along the beach can mislead. A long record of lines gives the shape. The payoff arrives. Acceleration is the curvature of the shoreline record, not a single wave. A new visual anchor makes the final synthesis physical rather than abstract. A broad void opens like a bowl. Its interior is smooth and dark. Along its rim, A filament forms a bright arc of galaxies. The arc has a thickness. It has a soft gradient. The density rises toward the filament spine. It falls toward the void center. At one end, the filament bends into a node. The node is a concentrated knot with a faint halo. The knot's outer edge is not sharp. It fades like smoke into the surrounding field. This boundary detail matters. Bound structures remain coherent. The empty space between them expands more effectively. The web becomes a set of stable knots linked by increasingly long bridges. Another payoff settles. The accelerating universe does not erase structure. It changes what counts as connected on the larger scales. The second concept returns also in its calmest form. Dark energy is a name for whatever drives late-time acceleration. The definition stays short. Dark energy is the cause of accelerated cosmic expansion. The name does not specify the mechanism. It is a placeholder for a behavior seen in the expansion history. A constant-like component is the simplest version. A slowly evolving field is another. Modified gravity can imitate the same distance curve while changing growth. The distinction is not philosophical. It is observational. It lives in the way distances, lensing, and clustering cohere. Another small understanding settles. A model becomes credible when it predicts multiple kinds of maps with one set of parameters. A single number provides a last foothold without crowding the mind. The switch from deceleration to acceleration occurs when the universe is several billion years younger than it is now, on the order of 5 billion years. That is like the midpoint of a long night. The sky looks nearly the same to casual glance. Yet the slow shift is real. It changes the long-term fate of connectivity. It also changes how far light can travel and still arrive. The payoff arrives. The most important number is not a speed. It is a timescale that marks when the balance of components tilts. A scale shift then softens the entire narrative. On a timescale of seconds, light behaves as a wave. It diffracts. It interferes. It spreads gently around small obstacles. On the timescale of millions of years, stars evolve and fade. On the timescale of billions of years, expansion changes the spacing between galaxies. These scales coexist in one picture. A photon's path is influenced by local curvature near a galaxy. It is also stretched by the global expansion of space. The same beam carries both the local and the global story. Another small understanding settles. The universe can be described as layered influences. Local gravity sculpts knots and halos. Global expansion sets the stage and slowly widens the gaps. Now a limit of observation arrives, and it is precise in spirit. Dark energy is inferred from light that has travelled across immense distances. That inference depends on calibration selection effects and assumptions about uniformity. It depends on the stability of standard candles. It depends on the mapping from redshift to time. It also depends on a cosmological model framework that links different observables. The limit is not that the evidence is weak. The limit is that some future behaviour cannot be directly checked. The far future horizon is a prediction, not a measurement. The detailed microphysics of dark energy is not directly sampled. It is reconstructed from its gravitational imprint. The boundary is clear. Knowledge here is indirect. It is disciplined by cross-checks. It remains open to refinement. Another gentle scene returns to the void bowl and filament rim. The rim's arc holds steady. The gradient from dense edge to empty interior stays smooth. The void interior remains dark and quiet. The knot at the filament end glows faintly surrounded by a diffuse halo. The halo has a soft outer boundary. It blends into the background. The image suggests a universe that is both structured and spacious. Another payoff settles. Acceleration adds stillness to the larger scale story. It makes the distant universe recede into quieter separations, while local structure continues its slow shaping. The final sentences offer a soft landing without suspense. The evidence remains a curve drawn from many faint lines. The models remain maps that are tested by how well they fit the whole sky. In that wide darkness, the web holds its shape. The gaps widen gently. The story becomes a calm geometry of distance and time,